The sonar return didn't make sense. At 1,600 meters, the submersible's instruments detected a horizontal surface. Not rock, not sediment, a liquid boundary, but the vehicle was already underwater. When the camera lights cut through the dark, the crew saw waves, slow, deliberate ripples lapping against something that looked like a shoreline, at the bottom of the Red Sea. Then a fish crossed the boundary. The sensors spiked. The animal convulsed, lost control, and sank, dead before it cleared the edge of the frame. Every organism that entered the lake followed the same pattern. Immediate failure, no recovery, except one. And what that creature is surviving inside, a chemical environment that should kill on contact, wasn't supposed to be stable, observable, or still there when researchers returned. We are taught that the ocean is a single, continuous body of water. Physics dictates that liquids mix. If you pour a cup of salt water into a bathtub, it dissolves. It doesn't sink to the bottom and form a separate, coherent puddle with its own surface tension, its own waves, and its own chemistry. Yet, scattered across the deepest abyssal plains of the planet, sonar operators have been picking up false bottoms for 60 years. Signals that indicate a hard surface where there should be open water. These aren't glitches, they are brine pools, underwater lakes that defy the laws of miscibility. They are some of the most toxic environments on Earth. High pressure, zero oxygen, methane concentrations so high they should sterilize any biological cell instantly. But the most disturbing part isn't the chemistry, it's the behavior. These pools aren't just stagnant depressions, they have shorelines. They have distinct coastlines made of mummified crabs, and as recent expeditions in the Red Sea have confirmed, they are traps. Tonight, we are going to 1,600 meters to look at the interface between the ocean we know and the alien ocean hiding beneath it. The first time this phenomenon was recorded, the data was largely ignored. It was 1964, the height of the Cold War. The British research vessel RRS Discovery was crossing the central Red Sea, running deep hydrographic lines. The oceanographer on board, Henry Charnock, was looking for temperature anomalies in the water column. He found one, and it didn't make physical sense. At 2,000 meters depth, the water temperature should be stable, around 2 to 4 degrees Celsius. But as Charnock's instruments hit the bottom of a depression known as the Discovery Deep, the temperature gauge spiked. 20 degrees, 40 degrees, then 44 degrees Celsius. At the same time, the salinity sensors went off the scale. Normal seawater is about 35 parts per thousand salt. The water Charnock found was 270 parts per thousand, nearly saturation point. It was 8 times saltier than the ocean above it. Charnock published a brief note in the journal Nature titled Anomalous Bottom Water in the Red Sea. He described it as a hot brine, but the scientific community treated it as a curiosity, a local thermal vent effect. They missed the scale of what he had found. He hadn't found a vent, he had found a boundary layer. A sharp, distinct interface separating the ocean from a massive volume of liquid that was heavier, hotter, and deadlier than anything else in the basin. For decades, these anomalous waters remained a footnote in oceanography. Why? Because without modern ROVs, remotely operated vehicles, you couldn't see the surface. You could only measure the chemical spike. It wasn't until cameras went down that we realized these weren't just chemical clouds, they were physical lakes with waves. To understand why this is terrifying to a physicist, you have to look at the thermodynamics. Heat rises, salt dissolves. A pool of hot, salty water at the bottom of the ocean should over time diffuse into the cold water above it. It's entropy. The universe wants to mix things. But these pools don't mix. They stay distinct for thousands of years. The mechanism keeping them stable is called double diffusive convection. It's a rare fluid dynamics phenomenon. Heat diffuses through water about 100 times faster than salt does. So at the surface of the lake, the heat escapes upward into the ocean, but the heavy salt stays behind. This creates a density trap. The water becomes so heavy, so laden with dissolved solids, that it behaves more like a syrup than seawater. The specific gravity is so high that a submersible or a submarine can't sink into it easily. It literally bounces off the surface. If a submarine tried to dive into a deep brine pool, the sudden change in density would violently arrest its descent. It would hit the surface of the lake like hitting a runway. But where did this water come from? It's not from the ocean, it's from the rock. Millions of years ago, the Red Sea dried up. It left behind massive salt deposits, kilometers thick, similar to the Messinian salinity crisis in the Mediterranean. When the ocean returned, it buried that salt under sediment. But tectonic pressure is squeezing it out. The salt dissolves into groundwater, heats up from the Earth's mantle, and erupts onto the seafloor. It is fossil water, ancient toxic fluid that has been trapped in the crust since the Jurassic period, and when it pools on the bottom, it creates a kill zone that nothing can survive, or so we thought. In 2020, the Ocean Explorer research vessel returned to the Red Sea. Led by Dr. Sam Perkins from the University of Miami, the mission wasn't relying on 1960s wire sensors. They had a high-definition ROV. At a depth of 1,770 meters, the ROV pilots saw it, a distinct line in the darkness. As they approached, the lights illuminated a sandy beach, but the beach wasn't on the shore of an island. It was 1.7 kilometers underwater. The sand was actually barite crystals and microbial mats, and lapping against it were waves. The footage is unsettling. You are looking at water moving underwater. The internal waves form because of the density difference between the brine and the seawater. They move in slow motion, rolling lazily against the shore. Dr. Perkins and his team maneuvered the ROV to the edge. The instruments read the environment instantly. Oxygen 0, salinity, saturation levels. Methane concentration 15 to 20 millimolar. For context, that much methane is usually explosive. Down here under pressure, it stays dissolved, turning the fluid into a toxic cocktail. But the visual data revealed something else. The shoreline was littered. It was covered in the preserved carcasses of crabs, fish, and eels. They weren't decomposing. The brine is so salty it pickles them, it mummifies them. Some of those bodies could have been there for weeks, others for decades. It was a graveyard that never rots. This is where the horror of the brine pool becomes clear. It acts as a trap. In the abyssal darkness, scavengers hunt by scent. The high concentration of methane and other chemicals wafting off the pool smells like food. It smells like organic decay, so predators swim toward it. Dr. Brad Sable, an expert in deep-sea physiology, explains the mechanism of death. It isn't drowning, it's toxic shock. When a fish swims across that interface, passing from normal seawater into the brine, the osmotic pressure changes instantly. The water inside the fish's cells is ripped out by the saltier water outside. It's cellular dehydration on a massive scale. Simultaneously, the high methane levels induce immediate hypoxia. The ROV cameras caught it happening. A fish wanders too close, it dips its head into the fog. Instantly, the nervous system misfires. The fish seizes. It thrashes wildly, but the convulsions just drive it deeper into the heavy fluid. Within 10 to 30 seconds, it's dead. And once it dies, it doesn't float away. The brine preserves it, adding its body to the beach for other scavengers to see. But there is one exception, one creature that breaks the rule. The hagfish Myxen glutinosa asterisk. Researchers watched in disbelief as hagfish swam directly into the toxic pool. They didn't convulse. They didn't die. They swam to the bottom, fed on the carcasses of the mummified victims, and swam back out. We still don't fully understand how. Their physiology is primitive. They are jawless, ancient vertebrates that haven't changed much in 300 million years. They seem to have an osmotic tolerance that defies modern biology. They treat the most toxic environment on Earth as a private pantry. If the hagfish are the visitors, what are the residents? Because the pool isn't empty, it's teeming with life, but it's life that shouldn't work. Clustered around the edges of these pools in the transition zone are vast beds of mussels. Thousands of them. There is no sunlight here, photosynthesis is impossible, and yet these mussel beds are dense, thriving ecosystems. Dr. Eric Cords from Temple University has studied similar cold seeps in the Gulf of Mexico. He found that these mussels don't eat in the traditional sense. They don't filter plankton, their digestive systems are atrophied. Instead, their gills are packed with symbiotic bacteria. These bacteria are methanotrophs. They eat methane. This is chemosynthesis. The bacteria take the toxic methane gas that would kill a human instantly, strip the carbon atom, and convert it into energy. They feed the mussel from the inside out. This discovery forces us to rewrite the definition of habitable zone. These organisms aren't surviving asterisk despite asterisk the toxicity. They are surviving because of it. If you took them to clean, oxygen-rich water, they would starve. They need the poison. And this has terrified astrobiologists, because we know of other places in the solar system that have ice-covered oceans, high salinity, and methane plumes. Europa, Enceladus. If biology can adapt to utilize a toxic brine pool at 1,600 meters in the Red Sea, it doesn't need a Goldilocks planet. It just needs a chemical gradient. The monsters in the brine prove that life doesn't need sunlight, it just needs fuel. The Ocean Explorer expedition didn't just map a seabed feature, they mapped a warning. We treat the ocean as a resource we can manage, but features like the NEOM brine pool remind us that there are pockets of this planet that are fundamentally hostile to us. The interface at 1,600 meters is a border. Above the line, the rules of our biology apply. Oxygen, sunlight, osmosis. Below the line, the rules change. It is an alien world located within our own, a liquid trap that has been waiting since the Jurassic period. Instruments can measure the salinity, cameras can record the waves, but we still can't explain why a hagfish can swim where a submarine would bounce or why life thrives in a chemical soup designed to kill. We look to the stars for aliens. We spend billions listening for radio signals, but the most alien organisms we have ever encountered aren't light years away. They are a mile beneath the waves of the Red Sea, swimming in a lake that shouldn't exist. If you want to see the raw footage of the underwater waves, click the video on the right. And if you think we should leave these pools alone before we wake something up, hit the like button. I'll see you in the dark.